Bonjour. Maintenant, on a de nouveau un journal international, mais assez différent. C'est écrit le groupe du Lycée de Durance à Pertuis. Et avec eux, et un exposé jumelé pour une fois, le groupe du Colegiul national Emil Racovita de Cluj-Napoca. Je suis désolé, je ne sais pas prononcer le roumain, mais qui vont vous présenter ce problème du collectionneur d'œufs en chocolat. Alors, le chercheur, je ne sais pas s'il y a deux chercheurs, mais enfin celui de Val-de-Durance, c'est Yves Papeguet. Et les encadrants, il y a Hubert Proal pour le lycée Val-de-Durance et Ariana Vacaretou pour Cluj. J'ai bien dit Cluj? Bien, et bien alors ça va être à vous.
Hi, I'm Alexis, and I will present you a work on probabilities did in cooperation between students from Pertuis High School and Romanian students to whom I give the speak.
Good afternoon, my name is Mara Vasiliu.
Good afternoon, my name is Jucan Codruța.
And together with the French students, we worked on the following research topic. Every day we buy a chocolate egg which has a toy inside. The toy isn't known before tasting the chocolate. This toy is part of a collection with a certain number of toys. After how many purchases can we hope to have the complete collection?
So at the beginning of our method, we introduced a new variable, k. We also have n, which is the number of toys in a collection, and k is the number of samples per toy. So, for example, n equals 3 and k equals 5. That means we have 3 toys in a collection, and for each of them, there are 5 samples, exactly like here, 5 cars, 5 dolls, and 5 figurines. So we noticed that the most favorable case for us to have the whole collection is when we buy exactly n toys, like when we buy the whole collection on the first try. And we also noticed by using the box principle that the least favorable case is when we buy n minus 1 multiplied by k plus 1 toys. And by buying that number of toys, even though it's the least favorable case, we can be sure that we will have the whole collection. And my friend Mara will explain why.
As an example, we took n3 and k5, so that means that the collection has 3 different types of toys, and each of them is produced 5 times. So in total, we have 15 toys. After finding the least favorable case with the formula that we presented in the previous slide, we have found out by using the box principle that we have to make 11 purchases. To break this down, we will suppose that we can control which toy we get. So first, we buy all samples of toy 1, in this case 5, and we have circled them with purple. Then we buy all samples of toy 2, again 5, and here are circled with blue. And afterwards, we only have to purchase 1 toy 3, and we have the complete collection. This means that we have to make 5 plus 5 plus 1, which of course equals 11 purchases.
Because we didn't have enough time to get to a final formula, even though we were close to it, we will explain an example we tested. When n equals 2 and k equals 3, that means we have 2 toys in a collection and 3 samples for each of them, and in total there will be 6 toys. One of them is toy A and the other one is toy B. So the probability for us to buy toy A on the first acquisition will be 3 over 6 because there are 3 toys A and 6 samples in total. Then the second acquisition, we could secondly buy toy B with a probability of 3 over 5 because there are 3 toys B and 5 samples in total left. And then the collection will be complete. Or we could buy toy A, another sample of it, with a probability of 2 over 5 because there will be 2 toys A left and 5 samples left in total. Then we could again buy toy B with a probability of 3 over 4 and the collection will be complete. Or we could buy the last sample of toy A with a probability of 1 over 4 because there is only 1 sample of toy A left and 4 samples left in total. After that, we could be sure that the next purchase will be toy B because there are no samples of toy A left.
On the other hand, if at first we buy toy B, which also has a probability of 3/6, since we have 3 toys B and 6 in total, then we can buy toy A and finish the collection. Considering we still have 3 toys A that we could buy and only 5 left in total, the probability that this would happen would be 3/5. Otherwise, if we buy one toy B again, the process goes on until we no longer have toys B left, and the only possibility is to buy toy A and complete the collection. The probability of this event happening after a set number of purchases, for example, 3 purchases, is the product of the probabilities of each purchase, such as 3/6, the first purchase, multiplied by 2/5, the second one, multiplied by 3/4, the last purchase, the one that completes the collection. Since we have 2 branches on our probability tree, we have to calculate the sum of the probabilities in both cases in order to find out the final one, which in this example is 3/10.
So for all the purchases, we are doing an approximation by calculating the sum of all the probabilities, like here. So for our example, after 2.5 acquisitions, we can be sure that our collection is complete.
On our side, we have chosen to consider the stock are unlimited, with n the number of different toys and a the number of purchases. So we look for what value of a we are sure to have the collection, that is to say 95% chance or more. To begin, we did a probability tree we were able to find the probability to obtain a specific branch was 1/2 to the power of a. Indeed, for the probability of this branch, after 3 purchases, we have to do 1/2 times 1/2 times 1/2, which gives us 1/2 to the power of 3. Then, like there are always 2 branches which do not give us the collection, we have to multiply the probability by 2. So we found a formula that gives us the probability of not having the collection in function of the number of purchases. Then we have just to subtract the result to 1 for the probability to obtain the collection. It's important to note that A has to be greater than or equal to 2 and has to be a natural number. But we did not find a formula that worked for any value of n. So we programmed a simulation that gives us a number of purchases, what is necessary to make a collection. Then we put this data in a graph that gives us a frequency to have the collection in a maximal of 8 purchases. That is to say, for example, for 4 purchases, we will do the sum of complete collection did in 2, 3, and 4 purchases. If we look at the graph, we see that after 6 purchases, we have more 95 chance to have the collection. This corresponds to the result found with the formula. When we look at the graph, we see that for 3 objects, it will take 9 purchases to be sure, it will take 20 with 5 objects, and 31 with 7 objects. Of course, it's just a simulation, and even if we did 100,000 simulations, it is not real results, so it's necessary to continue to search for a formula. That is for us. Thank you for your attention.
Yes, thank you. I have not many questions. Only one. Guillaume Rincel, what's the box principle? That's for the first part of the talk.
So the box principle says that if, for example, if we have 3, let me formulate this. I can show on the example so it's easier for me. If all of these toys were put in boxes, then we will take the all the toys in the first box, then the toys in the second one, and we have to make sure after so we buy all these 5, then this 5, and then we only need to buy 1. So if we were to put them all in a box, then we would only need to put this one. At least. I don't think that I have explained it well, so maybe my friend can say something better because I'm a bit nervous. Sorry.
Well, as Mara said, in this collection there are 3 toys and 5 samples for each of them. So the box principle says that if we buy 11 toys, as we did with the formula, then we will be sure that we will have all the collection, like at least one of toy 3, at least one of toy 2, and at least one of toy 1. Like we have to buy all of the toys 1, all of the toys 2, and only one of toy 3, for us to be sure that we have the whole collection. I don't know if I explained well too.
Well, I think you explained well, ok. Pour les francophones, oui, je crois qu'il y a 2 parties un peu différentes dans les 2 parties de l'exposé, puisque là, on a plusieurs jouets dans chaque œuf, disons. Et par contre, pour le lycée Val-de-Durance, on prend un à la fois, mais ce n'est pas si différent que ça. So, maybe for the second part of the talk, you said that for 3 different toys, you don't know how to compute different probabilities. Do you have something? Well, is it so difficult, or can you find some idea to begin? Even if you didn't have a final formula?
We tried many times, and when it worked for 3 to the beginning, but after it changed. We had formula who worked only for one number. So I think we had formula. No, she worked for the beginning of 3, but after we didn't know why it didn't work for n equal 10 or more.
Yes, but if we begin with n equals 3, well, if you have 3 different toys, A, B, and C, you can compute, as you did for the case of 2 different toys, you can compute the probability of not getting to toy A, of not getting to toy B, of not getting toy C, and maybe combining all that, you have a solution. I don't know. I just asked the question.
But no, we didn't find formula. Or we don't have. We had idea, but there were nothing idea who worked.
Okay, you need not to have all the solutions. That's an open question for people who listen. There is another question, maybe 2 questions, but more or less the same. If you are a very unlucky guy, how many purchases do you need to have all toy? Another question, is it possible to never get the whole collection? So I think that's different according to the 2 parts of the talk. Because in the Romanian part, the whole collection was finite, and you can, the French side of the topic here, you can buy indefinitely as many x as you find. Okay.
In all parts, like we have unlimited stock. If we are not lucky, yes, we can never have the collection, but it's really improbable, especially for a little number like 2, 3, and you see after it's really it's 100%. It's impossible with after 20 buying with 2 objects who don't have the collection. The probability is really small.
Yeah. Okay. I think you have the correct answer. It is possible to never get the whole collection, but the probability is 0. That's the answer. Okay.
Probability is never to 0 when stock are unlimited, but
yes, the limit. It goes. Okay, and in the Romanian case, you have a finite collection of toys.
Yeah, so if you're an unlucky guy, you have to buy this number of toys. Wait a second.
Mm-hmm.
By using the box principle, because this is the least favorable case, the unluckiest. If you buy this number of toys, you can be sure that you have the whole collection, because Mara explained it here that you have to buy all of the first 2 sections of toys and then only one of the other sample. But it can be possible to never get the whole collection if another person tries, for example, to buy it, and let's say they buy all the samples of toy 1, and then there are only toy 2 and toy 3 left, so you can't get the whole collection. But it depends on how lucky you are.
Yes, but yeah, I understood from your talk that you were the only guy to buy eggs, and you can buy the whole collection.
Yeah, kind of.
Okay. No matter. Okay, thank you a lot for your talk. There is another question. Did you study the case where there is more than one buyer? Yeah, that's exactly what we talked about just now. Okay, so thank you. Bravo en français. Merci à vous et à bientôt, j'espère.